Right, so looking at question 5, looking at solar panels, solar panel lamps. What these basically do is they store light energy from the sun and convert it into chemical energy, and then that can be converted back into light energy when it goes dark. So we've got a variety of different symbols. We've got to match them up with the components for 1 mark. So straight away, this is a cell. A cell is basically what we call a battery, but it's just one of them. So that's just a cell. A switch would be that one. A thermistor, which is something that is changes its resistance by the temperature, would be that one. And then an LDR, or light dependent resistor, is something that is dependent on the light that hits it. So a switch, to start with, that makes or breaks a circuit. Obviously, if it's switched on, the circuit's made. If it's switched off, the circuit's not working. A cell is the bit that transforms the chemical energy into electrical energy. A thermistor is varied with temperature, and then an LDR is determined with light. So the next question then looks at, well, if it comes on automatically in the dark, it might also have a manual override button when the lamp's not wanted. Which of the components is unlikely to be used? Well, it's unlikely to have a thermistor. Temperature is likely to have nothing to do with this actual circuit that's going to help the light come on or off or not. Question C. So the manufacturers can choose from 2 light sources, the lamps, either LEDs or filament lamps. The data in the table can be used to calculate the power. Now it says there to calculate the power of each light source. So this is actually linking back to P3 a little bit as well. So we've got, straight away, we've got a voltage and we've got a current. If you're struggling to figure out what the equation is for calculation, for power, look at the front, and we've got power is equal to voltage times current. Okay, so if we go back to the beginning in the question, we've got a power, we've got a voltage, we've got a current, we can work out the power. So if P equals IV, so power equals current times voltage, we can work out for the LED that 1.5 multiplied by 0.001 amps, so that would equal 0.0015 watts. And then for the filament one, we do exactly the same. We can take the 3 volts and multiply it by 0.5 amps, and that will give us 0.15 watts. Okay. Now that basically means that this one is got the highest power that one's got the lowest power. Now power is how quickly an object uses the energy that it's given to it. So to start with, them calculations would get you the 1 mark. What we need to say is well, let's compare the 2. So the LED bulb is going to waste less energy than the filament one. Okay, it's going to waste less energy than the filament one. Therefore, it is more efficient. So is more efficient. If you remember, the bulbs, all bulbs give off heat. So all bulbs give off heat, and the one that gives out the least heat is going to be the more efficient one. And obviously, the LED bulb, because it's got a lower power rating, it's going to waste less energy because it's going to use less energy as well. So what we're now given is we're given some data. So Angela sets up the solar panel lamp in a garden. Each month she measures how long the solar panel lamps remain on. She's got a graph. So in July, the average about 3.2 hours. August, slightly lower at about 2.7, 2.8, and so on and so on. So Angela concludes that the solar panel lamps, the less energy they can store. So Angela concludes that the older the solar panel lamps, the less energy stored. So if we buy one in July, and by December there's less and less light. So discuss her conclusion with reference to correlation and cause. So first of all, let's look at the actual correlation. What is a correlation? Well, as you can see, as the months go on, or the age of the bulb, the age of the lamp goes on, the average time does go down. So there is a negative correlation. That is one thing there actually is. There is a negative correlation. But that doesn't necessarily mean that that correlation is caused by the length of time. There might be some other factor that's actually affecting how long that light stays on. So there could, but this is not necessarily a direct cause. This is not a direct cause. another factor, so for example, light intensity may affect how long the lamp stays on, may affect the lamp. So obviously in July, August, it's more of summer months, the sun's out for a longer period of time, it's brighter, the lamp will possibly stay on longer. So it's actually, there might be a correlation, but it's not necessarily a cause due to that. Okay? Right, question 6. Question 6 is all about static electricity. So Tim walks on a nylon carpet wearing shoes with a rubber sole. So straight away he's telling us that there's two surfaces. We should hopefully realise that those two surfaces are insulators. And he touches a metal rail, and we should hopefully know that that is a conductor, the fact that it's metal. He's worried about these electric shocks. It says explain these observations, so it's saying explain the causes of these electric shocks and discuss whether he needs to what he needs to consider to decide if they're going to be a high risk or not. So the first thing we need to talk about is, well, what actually causes these electric shocks? So he says he's got nylon carpet and rubber soles. So there's going to be friction between the two insulators. Now this friction is going to transfer electrons between the two conductors. Between the two insulators. So transfer electrons between the insulators. And because they're insulators, there's nowhere for these charges to actually flow. Okay, so they stay charged. So they're either going to be negatively charged if they gain electrons, or positively charged if they lose electrons. Okay, so what happens is he's now charged. So Tim's walking along the carpet. The friction between his shoes and the floor is creating a charge. He's now become charged. When he touches the conductor, this charge can flow. And the reason why that's the case is if I was quickly just to draw the atoms within a metal or a conductor, they've got electrons that are called delocalized, which basically means that these electrons are free to move. Because they're free to move, that means they can conduct electricity, because electricity is just the flow of these charges. So, touches the conductor, the charges can flow through himself, and that is basically the shock, so causing the shock. Now, things to think about with this actual shock that it's getting. Many people experience these shocks. And they don't suffer from them in the slightest, okay? They're just shocks. They can be annoying, but they're not actually going to cause him any harm. So many people experience these shocks without any harm. But the only reason that it might cause serious damage is if he's got a major heart condition or he's got a pacemaker. So, however, if he has a heart condition, it could affect it, but the risk is low, really. And that is the end of the P5 section.